Hey guys, this video has been in the works since of early February, so if I sound a little bit robotic, if I left information out, or if the logic is outdated, I'm sorry in advance. If there is any point in the video where you are confused, feel free to ask questions in the comment section below, and I'll try my best to answer them. Thanks again, and I hope you get what you need out of this video. Hey, welcome back! In this tutorial, we will be implementing an idle, walking, and running animation to our mech template. Now, this is a continuation of the previous tutorial, so if you haven't watched that tutorial yet, or if you don't have a mech rigged with IK yet, I'd highly recommend to do so. Now, before we move on, I want to do some corrections to the previous tutorial, because I made a few mistakes, so please check this over on your side as well. I failed to mention, after you create your vector translation, you want to connect the number to the vector magnitude and the turret rotation handler, otherwise it won't work. Another thing where I did an oopsie was in the forward hip or shoulder servos. I multiplied the bottom part of the formula with our shin length when it was supposed to be our thigh length. So please, for the legs, replace the current connected shin length with our thigh length. And for the arms, replace the current connected forearm length with our arm length. Now that's over, let's move on. Before we get to the main part of the tutorial, let's do some modifications to our logic boards in order to prepare for animations. What we're going to do is make some sort of animation handler. We'll be using a technique called switchbox chaining. Now, how switchbox chaining works is that the preceding switchboxes will always have priority. For example, if you put your combo animations before the walking animations, if you try to walk during the combo animations, it will not work since the combo animation has priority and is playing the animation first. What we'll do is copy and paste the switch boxes from the testing board. Disconnect everything and copy it 2 times. The first column from the left will be our combo animations, the second column will be our running/walking animations, and the third column will be our idle animation. Connect them in a row to the off outputs like so. Afterwards, connect them to the off outputs on the testing board. And now we're ready to start. To start off this tutorial, we're going to learn how to set up a simple clock circuit. We will need a subtraction, numerical switch box, and a clock to make this work. Connect the clock to the off value of the numerical switch box and to the first value of the subtraction block. Next, connect the numerical switch box output to the second value input and to the on value of itself. For testing purposes, I connected the output of the subtraction block to a number display and a button to the switch box. We're going to activate it and see if it works. If you did correctly, whenever you press the button, it will start counting up. If anyone is curious how this works, basically when the numerical switch box is off, the clock subtracts by itself, resulting in 0. However, when you activate the numerical switch box, the numerical switch box will pause the clock and output as a clock time when you activated it. This means that when you activate the numerical switch box, the clock is subtracted by the clock time when you activated it, resulting in a clock that starts over every time you activate the numerical switch box. This clock circuit is very useful for animations, and we will be using it a lot throughout the series of tutorials. Now let's make the idle animation. Bring out a vehicle seat. If you open up the logic tool, you can see that there are 2 number outputs, a throttle and a steer output. If you move forward by pressing W when you're seated, it will output a 1. If you move backwards by pressing S when you're seated, it will output a -1. However, if you stay still, it will output a 0. Our clock circuit will be used for all animations. Whenever we meet the required conditions for a certain animation, the clock will run for that specified animation. For the idle animation, we want it so that it activates when our vehicle seat throttle is at 0. So you want to get an equal part and a constant part. Connect the constant part to the second value in the equal part, and connect the throttle of the vehicle seat to the first value of the equal part. Then, connect the equal parts boolean input to the numerical switch box. Now activate your build and see if it works. If you're not moving on the vehicle seat, the clock should run, but if you move forward or backwards, the clock should stop. Now before we move on, let's make a configuration board for idle animation. What we need is leg resting height, leg moving height, arm resting height, arm moving height, and animation speed. Resting heights will give your arms and legs that little bend while standing, and moving heights will make it look like your mech is breathing, making it move up and down very slowly. Animation speed is self-explanatory. For your resting heights, it will have to be a negative number due to how vectors work. If you want to give your limbs that little bend, it has to be a smaller number than your entire leg length. For example, since my leg is 33 studs long, I'll make the leg resting length negative 30. Okay, pause. Now, you gotta understand this part is really important. The reason why I say this is because our templates will look completely different from each other, so your values for the configurations will be different. Please don't copy my values and paste it onto your configuration because your configuration values will be based on the length of your template's limbs. We'll make our moving height 1 just for testing purposes. And now we do the same thing for our arms. We'll also make our animation speed 1. And later on, if we're not satisfied with the speed, we can change the animation speed to however fast we want. Before we get to our equations, add a multiplication block under the animation speed, and connect the animation speed to the multiplication block. After that, connect the subtraction output from the clock circuit into the multiplication block. Now, let's say that we want to make our leg go down straight. The coordinates for the position must be at x equals 0, y equals negative 33, and z equals 0. The closer we get to 0 for our y-axis, the more bend we get for our leg. If we want our leg to move, let's say from y equals negative 33 to negative 31 in a pattern, what math block would we use? If you guessed a sine block, then you are correct. A sine block produces a wave when the clock is inputted into it, going from 0 to 1 to 0 to negative 1 and then back to 0. And for future references, a cosine block does the same thing except it starts the pattern at 1 instead of 0. The formula for idle animation will look like this. So of course, since we're following BADMAS or PEMDAS, we will do the bracket first by inputting our animation speed into a sine block. After, we multiply the output with our moving height. Then, we add the offset with our resting height. Input the output into the y-axis of a number 2 vector. Now, we will be needing 2 number 2 vectors for both sides of the legs. After that, connect our number 2 vectors to their corresponding vector switch boxes for the animation handler. We'll do the same thing for our arms. Copy and paste the board, rename them, connect the correct constants, and put them in their corresponding vector switch boxes. After, get the conditioned boolean output that runs the clock, and connect them to the idle switch boxes. Unanchor and see if it works. If it works, the legs and arms should be going up and down like this. Let's say you want to add an offset to the leg so that they are slightly spreading their legs instead of just standing straight still. What we can do is add offsets to the x coordinate to spread the limbs. To know which axis you need to apply the offset to, go to the frame and see the orientation of the global to relatives. For example, since this global to relative has a z-axis facing forward and the y-axis facing upward, we can assume that the positive x-axis is towards the right. Since our global two relatives are facing opposite of the mech frame, this means that for the left leg we will have to apply a positive offset to the x-axis and a negative offset to the x-axis for the right leg. The same thing applies for our arms. Check and see which axis it's facing, and since it's inverted compared to the legs, we'll apply the positive offset to the right arm and the negative offset to the left. For our offset, we can experiment and do a constant of 3. Now connect the offsets to the x-axis of the number 2 vectors. Remember to apply a negative to the ones that need it. Now that's done, let's see if it works. If the limbs moved inwards, then that means that the offsets are inverted. We can solve that by switching the negative and positive offsets. Now we want our feet to be completely flat while our idle animation is playing, so we can do that by adding our knee and hip servos angles together. Then we subtract 180 with the angle product. Connect it to a switch box's on input, and connect our condition boolean output to the switch box's boolean input. Then we connect it to the angle input of our feet servos. Okay, well obviously this is wrong because our feet is now upside down. We can fix this by just changing the 180 constant to 0 or 360. Before we start the walking and running animations, we're gonna need another clock. Duplicate the clock like so, and for the condition boolean, we want it so that when our throttle is not 0, it runs the clock. We can simply do this by adding a not after the equal block from the idle animations clock. Now connect it to the switch box and test it. We have two clocks now, one that runs when we're not moving, and the other one that runs when we're moving forward or backward. We're going to duplicate the idle animation board, so move it aside and delete the feet section because we don't need it anymore. Let's delete the arm section as well for now because we're only going to work on the legs at the moment. Before we touch the leg logic board, let's change some things in the configurations. We'll rename leg resting height to leg height, leg moving height to leg stepping height, and we're going to add an extra constant and rename that to leg stepping length. Do the same thing for the arms as well. Delete the multiplication block under the animation speed, and now let's duplicate the configuration that we just edited. We're going to rename the duplicated configuration to running configuration, and we're going to rename the other one to walking configuration. Next, we're going to add some switch boxes which switches the configurations when you run. You only need switch boxes for the stepping heights, lengths, and the animation speed. Now for activating the switch boxes, we're going to use a keybind with a hold configuration on and change it to a keybind for running. I like to use left shift. Now connect the walking heights, lengths, and animation speed to the off inputs of the switch boxes. And after that, connect the running heights, lengths, and animation speed to the on inputs of the switch boxes. For our animation speed, connect the switch box's output to a multiplication block, and connect the walking/running clock to the same multiplication block. After that, we're gonna get another multiplication block and connect our seat's throttle output and the output of the previous multiplication block. We will be connecting this to our sine and cosine blocks. Now we're gonna start on our walking and running animation formulas. Do you remember my explanation for our sine and cosine waves and how if you input a clock into these blocks, it replicates a wave pattern? Keep that knowledge in mind while we're doing this part of the tutorial. We want to make our vectors to imitate a circular motion. Now I'll try to explain what I mean by circular motion that hopefully even a beginner could understand it. Imagine you're in a 2D axis grid with x and y coordinates, and that you're trying to draw a circle in the middle between 1 and -1 for both axes. If you notice, the lines do not touch the point in the middle, which is x equals 0, y equals 0. If you have a sine wave and a cosine wave run at the same time, you can notice that both of the lines will never intersect 0 at the same time. This meets the requirements of a circular motion in a graph. Using the information explained earlier with sine/cosine waves, we can basically get the same circular motion if we use the cosine block for our y coordinates and the sine block for our x coordinates, for example. The formulas we'll be using for our animations will be this. Putting that theory to test, let's implement the formulas for our animations. After we finish the formulas, connect them to their corresponding axis. We're gonna do the other leg now. All we need to do is duplicate the board we just completed and add a time offset to our clock by adding pi, like so. Connect our leg outputs to the animation handler. Let's test to see if it works. Now it's not working as intended. Make sure you connect your logic outputs correctly, unlike me where I connected the y-axis output to the z-axis of the number 2 vector. Also remember to change your configurations. This is where your frame might look a bit different from mine, so play around with the configurations, change the numbers to however you like. When you move forward, it should move like this. Now for the arms, duplicate the legs. Make sure you disconnect the leg settings and reconnect the arm settings. Also, remember that the side offset is inverse, so just switch it around. Connect the arms outputs to our animation handler. Now, when it's walking, it looks normal. However, when we start running, the arms move far too back, so we're gonna add a new configuration here. For this part, we're actually gonna move over our arm height and duplicate it over to our running configuration. We will rename this to arm bend, and we can modify this configuration to change how much the arm bends. We're gonna get a switch box and connect the walking arm bend to the off input and the running arm bend to the on input. We're also replacing the old connection by connecting the output of the arm bend switch box to the addition block of the y-axis for both arms. Now we're gonna add a forward arm offset, which changes how far your arm goes back or forward. If we want to save more parts, we can use the configuration settings inside the switch box itself using the configuration tool. So instead of connecting different constants to the switch box, we can change the on and off constants in the configuration tool. Now, if you duplicated the switch box from an already existing switch box, make sure to disconnect all the number inputs first before you changed any settings in the configuration tool. For the walking setting, which is off in the configuration tool, we don't want to change anything because it looks normal and we don't want to change that, right? However, since we want to change how the running looks, we're gonna add an offset to the running part, which is the on setting in the switch box. So I just added a random number to see how it looks first. Now that we have our switch box, get an addition block and put it in the z-axis. Connect the multiplication block to the addition block, and connect the newly added arm forward offset to the addition block as well. Disconnect the z-axis from the vector to number, and connect the output of the addition block that we just added to the z-axis. Now test to see if it works. Okay, now it's going even more back, which means we have to inverse the number that we just inputted. So instead of 10, we do -10. Now, if you want to restrain your arm from moving back, feel free to implement some clamps to your Y and Z axis for the arms, but I'm kind of too lazy to do that, so I don't bother. It looks quite stiff, so in order to fix that, we're gonna add some waist movement. Get a sign block and connect your animation speed output to it. What you need next is a multiplication block. We will be multiplying our sign with a constant that determines how much your waist weighs. Connect our multiplication output to the on value for our running/walking animation handler in the waist section. When we test it out, it seems that our waist movement is inverted. We want it to swivel right when our right leg goes forward and swivel left when our left leg goes forward. So all we need to do is just invert the angle in the constant. So I changed it from 45 degrees to negative 45 degrees. Okay, it looks better, but I feel like it's moving its waist too much, so let's change it from negative 45 degrees to negative 20 degrees. And now it looks completely better. For the running animation, I want to add some sort of lean when he's running, so we're gonna do that by adding a switch box. Connect the left shift keybind to it and change the on configuration to some sort of number. I did 20. Then we connect it to the upper torso's animation handler. Now he's looking upwards, which means I need to change the angle to negative 20 instead. Great, now it looks like he's running. Now that we have our animation down, we need to add our core servos. This is basically from the first tutorial that I've created, so I'm just gonna recreate that. We're gonna make some space for our animation handler to add in new sections that we will use for our core servos. Duplicate the switch boxes and make sure you reconnect them. We're gonna have an addition block which will connect to our core servos. Next, we need servos. We're gonna be moving our top servo into our frame's torso, and we're gonna leave the bottom servo floating in the air. Next, we resize them to a good size for your torso. Then we get our global to relative and put it inside our bottom servo. Make sure it's oriented like this. We also need to make our torque a large number for our servos, so don't forget that. Next, we get a mouse to 3D block, and we'll connect the vector output to the global to relatives input. Now we need a turret handler. We'll connect our global to relatives output into our turret handler's input. Then we connect the yaw to our addition block that connects to our core servo. Now we need aim parts to stabilize our servos. Now quick note, make sure the servos and aim parts are 10 density as well. On another note, make sure your aim parts are in the right orientation. Since the orientation of the servo is inverted, add a negative input before your addition block. So connect the yaw of the turret handler to the negative input, then reconnect it to the addition block. I'm adding more aim parts here to make the frame more stabilized. Now we need to negate the waist servo movement. To do this, we go to our animation handler and we connect the output of the waist from the running walking column to the on input of our horizontal core servos from the same column. Now all it did was add on to our swaying angle, so I'm gonna add a negative input in between the connection of our core servo switch box and the addition block. Now it's time to do our vertical core servo, which will negate the angle of our upper body servos. This is to prevent our whole mech from leaning backwards. Duplicate the logic from our horizontal core servo and delete these 3 blocks. Duplicate the horizontal core servo row in our animation handler and move it down. Let's not forget to rename the text blocks so we don't get confused. Disconnect our connection to the negative input and connect our vertical core servo output. From our animation handler, also disconnect the on input from the running walking column in our vertical core servo. Then we connect our running walking upper torso's output into the on input for our vertical core servo. I also inputted our negative input into our addition block again, just so we can have more lean forward. Oh my god, that's a mouthful. Now I'm gonna grab the core servos and duplicate them. We're gonna go use our rotate tool with the local setting selected and rotate it on its x-axis, flipping it to the side. The yellow indicator inside the servo should look like this. Now, disconnect the angle input, reconnect the addition block from our vertical core servo logic to the actual servo, and now we're gonna move our aim parts to the side. We're also gonna color code our core servos so it's easy to identify them. I colored my horizontal core servos red and my vertical core servos blue. Now, pay attention to our placements of our servos. I move my top vertical servo into the torso. I move the bottom vertical servo and compress it with the top horizontal servo. And for the bottom horizontal servo, I compress the aim parts and the global to relative together. You also need a lot of weight for the compressed servos, so get a head mesh, make it non-collide and 10 density, and add a lot of that to the compressed servos. One more thing to do before we finish is that we need to make sure that the properties of our feet are the proper settings that will allow maximum traction between the floor and our feet. To do this, make your elasticity and elasticity weight really low. After that, make the friction and the friction weight as max as it can go. So that's basically it for this tutorial. Depending on the size of the mech, it can reach a really high speed when it's running. I know this tutorial was a long one, but I hope you got what you needed out of this video. The next tutorial will be about implementing animations which are activated using a keybind, and it uses lists which should keep the part count down. So stay tuned. Bye bye. Yeah.